Welcome to this explainer on AP Chemistry Unit 9.9. Today, we're going to completely demystify electrochemical cells, and more importantly, the core calculations you absolutely need to master for exam day. I'm honestly thrilled to walk you through this material, because once you start seeing the visual patterns here, these concepts just click. We're going to break down exactly how chemical energy converts to electrical energy and vice versa.
So we're going to start with the absolute most fundamental question of thermodynamics. Will this specific chemical reaction act like a working battery entirely on its own? You know, in chemistry, when a reaction happens without any outside intervention, we call it thermodynamically favorable, or spontaneous. But how do we know, just by looking at a chemical equation, if it's going to power our devices or if it's just going to sit there in a beaker doing a whole lot of nothing?
Well, here is our roadmap for today. We'll be looking at galvanic cells, calculating cell potential, free energy, electrolysis, predicting products, and wrapping up with some AP practice calculations. Let's just dive right into step 1. Section 1. Galvanic cells.
Okay, galvanic or voltaic cells. These guys are thermodynamically favorable, and they act exactly like the spontaneous batteries we use every single day to power our phones and laptops. To understand how they generate electricity, you really just need to remember one quirky but super powerful mnemonic: fat cat. This tells us that electrons always flow from anode to cathode, and while those electrons are zooming through the wire, cations flow to the cathode and anions flow to the anode through the salt bridge just to balance the charges. Think about it. If the anions didn't replenish the negative charges as electrons are lost, the whole battery would just instantly stop working.
Now, as chemists, we love a good shortcut, right? So we use this shorthand called line notation to draw these cells out without having to sketch two whole elaborate beakers. In line notation, the anode is always written on the left, the cathode is always written on the right. And those double lines in the middle, that just represents the salt bridge connecting your two half cells.
All right, moving on to Section 2, calculating cell potential.
Let's get into calculating the actual standard voltage our spontaneous battery is going to produce. To find the standard cell potential, or E cell, we use this absolutely crucial formula. You simply subtract the anode's standard reduction potential from the cathode's standard reduction potential. And, actually, write this down because it's a classic trap on exams. Multiplying half reactions to balance your electrons does not change the magnitude of the voltage. You literally just pull the numbers straight from the table and plug them into this equation. If the resulting voltage is positive, congratulations, you've got a spontaneous reaction on your hands.
When you're looking at a standard reduction potential table, it's essentially a cheat sheet for how your chemicals want to behave. The substances up at the top left, like chlorine gas and oxygen, they have highly positive voltages. That means they are extremely likely to be reduced, making them excellent oxidizing agents. Meanwhile, the ones way down at the bottom, like your sodium and potassium ions, have very negative voltages. They absolutely hate being reduced. Therefore, they're the most likely to be oxidized.
Section 3. Free energy.
Let's tie that cell voltage we just calculated directly to thermodynamic favorability using our good old friend Gibbs free energy. Here's a rule of thumb you absolutely need to memorize for exam day. Standard Gibbs free energy, delta G, equals negative N times Faraday's constant times the standard cell voltage. That N represents the moles of electrons transferred in your balanced equation, and Faraday's constant F is 96,485 coulombs per mole of electrons. This single equation is literally the ultimate bridge linking electrochemistry straight over to thermodynamics.
To nail this calculation flawlessly every single time, you just follow 4 simple steps. Find your half reactions, determine your moles of electrons, plug it all into our equation, and then, this is key, check your units. The units cancel out beautifully when you remember one vital fact: 1 volt is exactly equal to 1 joule per coulomb. Now, because your answer is going to spit out in joules, step 4 reminds us that you must ultimately divide by 1,000 to get kilojoules, which, of course, is the standard unit for Gibbs free energy.
Which brings us to Section 4, electrolysis. Now we're going to totally flip the script. Let's look at what happens when a reaction is non-spontaneous, which is basically like plugging a dead battery into the wall to recharge it. Galvanic cells are spontaneous. They're separated into 2 containers, and they are a working battery that generates electricity. Electrolytic cells, on the flip side, are non-spontaneous. They happen in a single container, and they need an external battery or power supply just to force a chemical change to happen. Let's see how this builds on what we already know. While electrons still flow fat cat from anode to cathode, the polarity of the electrodes is completely reversed in an electrolytic system.
The cathode is now negative and the anode is positive. So just lock this mnemonic in your brain. EPA, electrolytic positive anode. If you know EPA, you won't get tricked on any of those tricky polarity questions.
Section 5. Predicting products.
So if you're performing electrolysis with an aqueous solution rather than a pure molten compound, things get a little sneaky because water is a competitor that might react instead of your target ions. While you could check a reduction table to figure out the exact chemical changes by comparing voltages, memorizing these two rules for aqueous solutions is going to be so much faster for you on the exam. First, Group 1A and 2A metals, like sodium or potassium, they won't reduce. The water will reduce instead to form hydrogen gas. Second, complex polyatomics like sulfate won't oxidize. The water will oxidize instead to form oxygen gas.
All right, final section, Section 6, AP Practice Calculations.
Let's put all the pieces together into an actual AP-style practice problem. Take a look at this overall reaction. In this specific electrolytic cell, we're using an electrical current to force pure liquid sodium chloride to separate out into liquid sodium and chlorine gas. Now notice the little L state symbol there. This is molten sodium chloride. No water is present, which means we don't have to worry about our aqueous rules at all.
To find out how much energy this takes, let's calculate the required voltage. First, we identify our cathode's sodium reduction potential from the standard table, which is negative 2.714 volts. Then, we find our anode's chlorine reduction potential, which is positive 1.36 volts. Using our trusty formula, we simply take the cathode and subtract the anode.
And wow, the math gives us a massive negative 4.07 volts. Because that number is negative, it tells us immediately that this reaction is highly non-thermodynamically favorable on its own. It's for sure not going to just happen by sitting in a beaker. Therefore, because the reaction isn't thermodynamically favorable, we literally have to supply at least 4.07 volts of electrical energy from an outside source just to make it proceed. You basically have to push back against the chemical's natural tendencies with 4.07 volts of force to break that sodium chloride apart.
Before we wrap up this explainer, let's test your true mastery of thermodynamics with one final provocative question. How would the voltage change if our half cells were made with 2.0 molar solutions instead of the standard 1.0 molar? Think about how Le Chatelier's principle might apply to cell potential when we shift those concentrations away from standard conditions. Keep pondering that, keep practicing those calculations, and I'll see you in the next explainer.